guess we'll get started. So last time we talked about Abelian varieties over the complex numbers, and we saw that they were all just complex tori. You could write them as vector space model lattice. And that made it very easy to figure out a lot of things about them. You could just work with those groups directly. So today we're going to talk about Abelian varieties over general fields. And many of the things that were true over the complex numbers are still true over general fields, but the proofs tend to be more complicated and different because you can't use that uniformization. So they're a little too involved to do completely for us because we don't have that much time. But in fact, the hardest parts tend to be statements that are true for general varieties. So we can kind of deduce all the stuff that, the special arguments for Abelian varieties are not that long on top of the general statements. Okay, so I guess throughout the day, K is going to be a field, and typically A will denote an Abelian variety over K. So the first thing to prove, again, is commutativity. That's the most basic fact about Abelian varieties. And you can prove it in a manner similar to how we did it over the complex numbers by looking at the adjoint action. But I'm not going to do that. I'm going to give a different proof that actually proves more. So the key statement that you need, which is a general statement about arbitrary varieties, is the rigidity lemma, which says the following. Suppose that you have varieties x, y, and z, and x is complete. And you have a map of varieties from x times y to z. With the property that its restriction to two axes is constant. So f restricted to x times some y0 is constant, and the restriction of f to, say, x0 times y is constant. For some, okay, these are varieties, x is complete, x0 is a point in x, y0 is a point in y. Suppose you have this such that, then f is constant. Okay, so from this we can prove the following. I guess I'll just state it as a corollary. So suppose that A and B are Abelian varieties, and F is a map of varieties. Such that f of 0 is 0. Then F is a homomorphism. So as long as you preserve the origin, you're a homomorphism. And the proof is just to consider the map, I'll call it H, from A times A to A, which is the sort of discrepancy of F to be a homomorphism. So H of x, y, I'll define to be f of x plus y minus f of x minus f of y. We don't know yet that A is commutative, but I'm still using additive notation for the group law. So then if you look at H of x is 0, that's f of x minus f of x minus f of 0, so that's 0. And similarly, that's H of 0, y, for all x and y. So this rigidity lemma then implies that H is constant. And since it takes the value 0, it's equal to 0 everywhere. And that exactly implies that F is a homomorphism. And corollary of the corollary is that Abelian varieties are commutative. And the reason is that if you look at the map from A to A, given by x goes to negative x, this takes 0 to 0. And so it's therefore a homomorphism, and that implies commutative. whenever you have a group, if inversion is a homomorphism, the group has to be commutative. Yeah. Did I? Okay. Yeah, that's right. Good catch. So I guess the proof actually shows that everything is a homomorphism and an anti-homomorphism, which gives you proof. Yeah. All right. So sort of the hardest part of these arguments is this rigidity limit, which is true for any variety, any setup like this. But the proof of that isn't actually so hard. If you look in Mumford's book, there's a proof. Okay, so the next thing to do, I guess, that you maybe want to do is to establish the structure of the end torsion. And that's going to take a little while. So first, we're going to need an intermediate result, which is another kind of rigidity result, which is called the theorem of the cube. This is, again, a general statement. So we have three varieties, x, y, and z. And x and y are complete. And we have three base points, x0 and x, y0 and y, and z0 and z. And we have a line bundle in the product. Okay, and suppose that L restricted to each of the sort of axes is trivial. So L restricted to x times y times z0, L restricted to x times y0 times z, and L restricted to x0 times y times z are all trivial. Then L is trivial. And just a little remark, giving a line bundle on scheme is the same as giving a map from that scheme to the classifying space for line bundles, which is the stack BGM. So you can rephrase this theorem just in different language, and it's saying that if you have a map, so this says that a map from x times y times z to BGM, which is trivial on the three axes, I'll call them, is trivial. So when you say it that way, it looks a little more like the rigidity limit that we just proved, but now it's for the target as a stack instead of a variety. But because it's a stack, you need three factors in the product instead of two. I don't know. I'm not sure, actually. I haven't thought about it. The question was, could you replace the GM there with, say, GLN or another stack? Okay, so here's an easy corollary. So let A be an abelian variety, and let Pi be the projection map from A times A times A to A, where I, 1, 2, or 3. And let Pij be the sum of Pi and Pj, and P1, 2, 3 be the sum of P1 plus P2 plus P3. Then if L is a line bundle on A, if L is a line bundle on A, then some big expression involving the pullbacks in all kind of possible ways is going to be trivial. P123 star L, tensor P12 star L inverse, tensor P13 star L inverse, tensor P23 star L inverse, then tensor P1 star L, P2 star L, tensor P3 star L is trivial. And this follows immediately from the theorem of the cube, just by restricting to a times 0 or a times 0 times a, things like that. You see, if you restrict to, so proof is sort of immediate. So I guess notice that when you restrict to, so on a times 0, P123 star is just equal to, so P123 star L is just equal to P12 star L. If we put 0 into the third slot. And P13 star L is just equal to P1 star L. And P3 star L is just trivial. So if you look at this expression, when you restrict this, things just match up and everything just cancels. So this P123 star turns into P12 star, which is going to cancel this P12 star with the inverse there. And each term just matches with another term and cancels. So that's all there is to this corollary. And so sort of a corollary of the corollary, just kind of a way to rephrase it that's going to be more useful. Suppose that we have maps FGH from some variety x to a. So x equals any variety. A is an abelian variety. And L is a line bundle in A. Then the statement is that a similar expression like this, where you put in sums of FGs and H's, is trivial. So I'll just write it out. This thing is trivial on x. It's a line bundle on x is trivial. This thing here is a line bundle on a times a. And the proof of this corollary is you just apply the previous one, and you consider the map from x to a cubed given by FGH. That's all there is to it. Okay, so now we can use these kind of crazy looking statements to get something that looks a little more reasonable. So suppose that L is a line bundle on the abelian variety A. Then we have the multiplication by n map, which goes to A. We can pull back the line bundle L by this map. And this theorem, or the corollary there, allows us to compute what this is. So it's equal to L to the n squared plus n over 2, tensored with the pullback by minus 1 of L to the n squared minus n over 2. And so two cases that are important to notice. If L is symmetric, meaning it's pulled back by minus 1 as itself, then this thing becomes the same as that, and so you can just add the exponents, and you find that n star L is L to the n squared. And if L is antisymmetric, course, just means that it's pulled back by -1 as its inverse. Then the two exponents you subtract, and so you get the pullback by n star L. It's just L to the n. So to prove this, we're going to apply this corollary over here. And we're going to take f to be multiplication by n, g to be multiplication by 1, meaning the identity map, and h to be multiplication by -1. So if we look at this expression and just write what it is, so f plus g plus h is just n, because 1 plus -1 is 0. So we find that n star L tensored, so f plus g is n plus 1, and this one has an L inverse, and then f plus h is n minus 1, and then g plus h is 0, and when you pull back by 0 it's the trivial bundle, so we can just leave that out. And then we have the pullbacks by f, g, and h separately. So, oh, this should be a -1 here. So n star L, tensor L, tensor -1 star L. So we see that this thing is trivial. And I'm going to write that in a nicer way. So i.e., so I'm going to move the n plus 1 to the other side. So n plus 1 star L is equal to what's left. And notice that there's two n star L's, so I'm going to turn that into n star L squared. So I have all of these, and then just these three left. So tensor n minus 1 star L inverse, tensor L, tensor -1 star. And so this lets you compute n plus 1 star L in terms of these other guys. And so you can just proceed by induction. So for example, if you put n equal to 1 in this formula, here you get 2 star L. And over here you get 1 star L squared, which is L squared. This is 0, so that goes away. Here's another L. So together these things give you L cubed. And then there you have -1 L, which is what you're supposed to get. Okay, so finally we can use this to actually say something much more concrete. We can use this to conclude that multiplication by n is an isogeny. And remember, that means it's surjective and has finite kernel. So the first step in the proof is to choose an ample bundle on L. Sorry, choose an ample bundle L on our abelian variety A. So to do that, you need to know that abelian varieties are projective. So you have to prove that first. I'm not going to do that. We did that over C with the Appel-Humbert theorem. But okay, you either have to just assume that abelian varieties are projective, put that in your definition, or prove that first. I'm not going to go into that. Okay, so we have an ample line bundle L on A. And now if we replace L by L tensor -1 star L, so since -1 is an automorphism of A, when you pull back L by this automorphism, it's still going to be ample. So pull back an ample bundle by an automorphism, it's ample. And the tensor product of two ample bundles is ample. So if we replace L by this bundle, we can assume that it's still ample and that it's symmetric. And so now we can apply this. If you have a symmetric guy, then when you pull back by n, you just get L to the n squared. And in particular, that implies that the pullback by n of L is ample, because it's L to the n squared. But when I take this pullback, n star L, and I restrict it to the n torsion, it's obviously the trivial bundle, because multiplication by n on the n torsion factors through the map going to 0. So it's just pulling back by a map to a point. And the pullback bundle is still ample. So this pullback bundle is both the trivial bundle and ample. So that means that on A of n, so A of n is a proper variety, or a proper scheme if you want to use the scheme theoretic fiber, because it's a closed subset of A, which is proper. And it has the property that the trivial line bundle on it, meaning the structure sheaf, is ample. And it's just a general fact that if you have such a scheme, it's 0-dimensional. Because on a proper thing, the trivial thing doesn't really have many sections. So for it to be ample, you have to just be a bunch of points. This implies that the dimension of A of n is 0. So in other words, the kernel of multiplication by n on A is finite. That's what this means. And since multiplication by n is a homomorphism from A to A, and it has finite kernel, it has to be surjective, because the image is going to have the same dimension as the source. So this implies that n is surjective also. Are there any questions so far? Okay, so it's good to know that multiplication by n is an isogeny. But of course, we'd want to know a little bit more. We want to know what the degree of that map is. Over the complex numbers, we computed it, because we know the size of the n torsion is just n to the 2g. And so that's the degree in general. It stays true. So this isogeny has degree n to the 2g. That's always true. And it's not hard to give a proof if you're willing to use some intersection theory. So here's a general fact. If you have a finite surjective map of varieties of the same dimension n, and you have divisors d1 through dn on y, so these are codimension 1 things in y, and there's n of them, n being the dimension. So you can intersect all of them in the sense of intersection theory, and you'll get something 0-dimensional, which you can think of as a number. So I can form this intersection on y, like that. Or I can pull these divisors back to x and do the intersection there. And the statement is that these are equal, but you have to put the degree here. And so if I work on my Abelian variety A, if I let D be a symmetric ample divisor in A. So by symmetric and ample, I just mean that the associated line bundle has those properties. So I'm going to look what happens when I do when I take F to be multiplication by n and use this formula. So what we know is that when I pull back the divisor by n, that's equal to n squared d, or linearly equivalent to n squared d. We know that on line bundles. Maybe I'll write three equal signs. Three lines are linearly equivalent. And so if I put that in here, you get the degree of n times the self-intersection of d with itself n times is equal to the self-intersection of n squared d with itself. Oh, sorry. Maybe it's better if I call the dimension g, because that's what I'm doing for abelian varieties. So there's supposed to be g of these divisors. And so I'm doing the self-intersection g times here. G is the dimension of any. So this intersection product is multilinear. So the n squareds pull out, and there's g of n. So you get n to the 2g out front. And the self-intersection number of d with itself, it's an ample divisor, so it gives you an embedding into projective space. That's just the degree of the image as a subvariety of projective space. So it's non-zero. So this implies that n to the 2g is the degree of n, since this number is not zero. Are there any questions about this proof? All right, so we're kind of getting closer and closer to what we knew we were seeing. We know the degree now. So we'd actually like to know the structure of the n torsion as a group. And there's not actually much more that we need to do to get there. So it's not hard to show that the multiplication by n map induces multiplication by n on the tangent space at 0. And so in particular, if n is prime to the characteristic of the ground field, this is an isomorphism of the tangent space. And you can use that to show that the map is separable. So n is separable if and only if n is prime of the characteristic. So I explained this in a little more detail for elliptic curves, but it's a similar sort of reasoning that works here. And so we can say then, I mean, if n is separable, then its kernel is a reduced subscheme. And so the number of field points is actually the degree. So that means that, so I guess what I want to say is, implies that if n is prime, implies. So if n is prime of the characteristic, the n torsion subscheme actually has the correct number of geometric points. Degree. And since this is true for all n prime to the characteristic, if you do this induction argument that I kind of briefly sketched for elliptic curves, this actually gives you the structure of this thing as a group. Z mod n to the 2g. And now the multiplication by p map is not separable. So if you look at its geometric points, I mean, there can't be, I mean, it has to be fewer than what you would expect from just the degree. So this is strictly less than p to the 2g. Remember in the elliptic curve case, the actual p torsion was 0 or 1 dimensional over z mod pz. So just from it not being separable, you get this. But in fact, this number is really less than or equal to p to the g. And we'll prove that when we get into group schemes a little bit more. So in the elliptic curve case, the p torsion was either 0 or 1-dimensional over z mod pz, the actual points. You had supersingular and the ordinary were the two possibilities. In this case, it's a lot more complicated. There's a lot more different behaviors that can happen. I mean, it's obvious that you can get any quantity between 0 and p to the g just by considering products of ordinary and supersingular with the curves. Okay, so there's one more application of this theorem of the cube, which I want to mention, which is the theorem of the square. So this is something that we proved over the complex numbers, but now we're going to get a proof of it in general. So L is a line bundle on A, and X and Y are 2 points in A. And the statement is that so T of X, little t is going to denote translation by this point. So I can pull back by translation. Tensor with L, and this is equal to Tx star L tensor Ty star. And the proof is just that corollary that I had written up there with the F, G, and H. You just take F to be the identity map, G to be the constant map that goes to X, and H to be the constant map that goes to Y. And if you just plug in, this is exactly what you get. And so you see that if you tensor each side here with L to the minus 2, this is going to turn into L to the minus 1. You can put an L to the minus 1 here and an L to the minus 1 here. So that means that if we define phi sub L of X to be pulled back by translation tensored with L inverse, then this thing regarded as a map from A to pick of A is a group homomorphism. So that's basically equivalent to this theorem of the square. Any questions? Yeah. Well, Tx is the map from A to A, which takes a point T to X plus T. Translation by X. Okay, so the next thing to talk about is the dual variety. So if you remember from last time, if we had an abelian variety that we had written as some vector space V mod lattice M, we define the dual variety A dual to be the conjugate dual space V mod the dual lattice M dual. So this definition is only going to work over C because it involves lattices and vector space quotients like this. So we'd still like to have a theory of the dual variety over an arbitrary field, but we need to find a different definition. So the key to doing this is to interpret A dual in terms of line bundles on A. So if you remember last time we had, this is still last time, we showed that there was a bijection from A dual to pick not A. And so pick not A is defined in terms of line bundles, so that looks good. But if you remember the definition of pick not we gave last time, it was those line bundles that were topologically trivial. So that definition of pick not doesn't carry over because it uses topology. But we had given a different characterization of pick not as the translation invariant line bundles, and that does carry over. So that's going to be how we get at the dual in general. So the sort of official definition is we're going to define pick not to be the set of line bundles L pick A such that your pullbacks are isomorphic in your translation. And so based on this bijection, we want an abelian variety A dual such that sort of as groups you have an isomorphism like this, just maybe as abstract groups. So in other words, we want the point set of the underlying thing here to be pick not A with the group structure given by tensor product. Of course, you can't define a variety just by giving a set of points. You can do it by giving its functor of points. So let's try to give the functor of points of pick not A. So for a variety T, and you could do this with the scheme as well if you prefer, but it doesn't matter. I'm going to define a functor. Its value on T is going to be the set of isomorphism classes of line bundles L on the product of T with A that satisfy two conditions. So the first condition is that when you restrict to any point in T, so you get a line bundle in A, and that line bundle should be in pick not. And the second condition is that if you restrict to the zero section A, you should get the trivial bundle of T. So notice that this functor is evaluated on spec K is equal to pick not A. So that looks like what we want. So we're going to define the definition. A dual is the variety that represents F. If it exists. And so something to notice, assuming that this variety exists, I mean, the way that representable functors work is it's not just an object that represents the functor, but it's an object and a universal object in the functor evaluated on the representative object. So if this functor is representable, then you actually have an object A dual and a universal object in F of A dual. So if A dual exists, it comes with a universal bundle P in here. So, i.e. a line bundle P on the product. And it's universal in the sense that, I mean, it sort of satisfies some property that looks like this, but as a special case, you see that mapping a point T in A dual to the restriction of this bundle to that point gives a bijection from pick not A to the points of A dual. I got that backwards. So that's one sense in which this bundle P is universal. P is called the Poincare bundle. So you'd like to know, I mean, this is just a definition. It doesn't actually show that A dual exists. In fact, it always does. So, fact, A dual exists. And let me just quickly give a very brief sketch of how you can go about finding this variety A dual. So how to find it. So pick an ample bundle L. Ample bundle on our abelian variety A. Then we have this map phi L that I've defined a few times now, which goes from the points of A pick not of A. Now, if you remember over the complex numbers, this map we showed was actually an isogeny of complex tori. And you can prove in this situation, this takes work, but you can show that this map is surjective and it has finite kernel. I'll call the kernel K of L. So at the moment, I'm just thinking of this as a map of abstract groups. I'm not even thinking of A as a variety in any sense, just an underlying point set. So this kernel is just a set of points. But if you think a little harder scheme theoretically, you can put a canonical scheme structure on K of L. So you can endow K of L with a scheme structure. It might be a non-reduced subscheme of A. And so this is a surjection with kernel K of L. So pick not of A should be A mod K of L. And A mod K of L you can give the structure of a variety. It's the quotient of a variety by a group. So it looks like you should have A dual should equal this. And so you can make that definition that gives you a candidate for A dual, and then you can prove that it does represent the functor. So that's one way to go about finding this variety. So there's another way to think about the dual, which is kind of neat, and I think will be useful for us in a little while. So suppose that we have a bundle and pick not. So by definition, that means that L is translation invariant. So I can choose for each point an isomorphism. I'll call it phi x from the pullback of L to L. And now you can look at, there's some compatibility that you might expect for these for different x's. And you can look if that indeed holds. So if you look at the pullback by x plus y of L, so this is very canonically the same thing as first pulling back by x, and then pulling back by y. So phi of x plus y goes down to L, just by definition. And then you can do T of x star of phi y, and that will go to Tx star of L. And then you have phi of x here. So you might expect or like that this diagram commutes, but it obviously doesn't have to because we just picked these phi x arbitrarily. You can scale them by numbers and it will ruin commutivity if you had it. So let's look at the discrepancy of it to commute. So I'm going to define, okay, so if you do phi of x plus y, and that's going to be equal to this composition up to some automorphism of L. Right? Because if you go around, you'll get some automorphism of L. So this will be equal to alpha of xy times for some automorphism, alpha xy in aught L. Does this make sense? Everyone following? I just have two isomorphisms from here to here, so they have to differ by automorphism. That's all I'm saying. Now the automorphism group of L, since it's a line bundle on a connected projective variety, is just the multiplicative group. And just because of the way that we've defined alpha xy, sort of just obviously satisfies the two co-cycle condition. In the sense of group cohomology. So we have A acting trivially on Gm. This just satisfies the two co-cycle condition for formal reasons. And so that means that it corresponds to a central extension of A by Gm. So 1 Gm. I'm going to call the thing in the middle script G of L. And this maps to A. For those that don't like group cohomology and things, here's another way to get this group. So there's three maps from A times A to A that are of interest: the multiplication map M and the two projection maps P1 and P2. So you can show that a line bundle is in pick not if and only if its pullback by multiplication is equal to the product of the pullback of the two projections. Well, isomorphic too. Been very sloppy with writing equals for isomorphisms of line bundles. So if we have something in pick not, then we get this isomorphism. And that's an isomorphism of line bundles in A times A. So if you look at what this isomorphism means at the point x comma y, it's really giving you a canonical isomorphism between x plus y, the fiber at x plus y, and the tensor product of the fibers above x and y. And you can think of this as a map from, so this is, think of L as the total space of the line bundle. So here we have, you could put okay, so you have this isomorphism. Of course, you can convert that into a map like this. Just change the tensor product to times sign and look at pure tensors. So this is a map from the fiber above y times the fiber above x, just two random points, to the fiber above x plus y. So in other words, this thing here is a map from L times L to L, which lifts the multiplication map on A. So from this condition, you get this map. And then you can take this G of L is just L minus the zero section, equipped with that multiplication. So this kind of tells you exactly what G of L is as just an abstract variety. It's just L minus the zero section. So this is a nice group variety. And in fact, it's true that this G of L is a commutative group. So this construction gives you a map, G, from pick not to the group of extensions of A by Gm, where this x1 is taken in the category of commutative group varieties. And Sayre showed that it's a bijection. G is an isomorphism of groups. And so the thing on the left and right were just individual groups. This is just the group of line bundles on A, and this is just the group of extensions here. But if you work with, varieties represent functors on the category of varieties, which are actually sheaves. If you take X in the category of sheaves of groups, you can recover the sheaf for A dual by this construction. But I'm not going to say anything more about that right now. Are there any questions? Okay. All right, so the next topic I want to discuss is the Moore-Delvey theorem. So this theorem says the following. If A is an abelian variety over the number field K, then the group of points is finitely generated. Key point here being the thing that I abbreviated to finitely generated. And the proof of this theorem is usually done in 2 steps. So first you show that A of k mod n A of k is finite for integers n. This is called the weak Moore-Delvey theorem often. And then 2, you deduce the full theorem from this using height functions. So I'm not going to say anything about 2, but I want to go over the proof of 1, because we're going to use the same ideas later. So proof of 1. So the idea is really to use Kummer theory. So the Kummer sequence is just this exact sequence. So A of k bar, that's the k bar points of A. That's an enormous group. And then here I have and since A is a divisible group, multiplication by n is a surjection of groups. So that's why I have surjectivity here. And then this is just the n torsion. So this thing here is isomorphic to z mod nz to the 2g. But the important point is it has a Galois action. GK acts on that. So this sequence here is usually called the Kummer sequence. And Kummer theory is just a name for what happens when you take Galois cohomology of this sequence. So let's look at what happens. So Galois cohomology. I'll go a little slow, I'll write out the whole thing. So we start with h0. And when I take h0, it's just taking k points instead of k bar points. It's the points fixed by Galois. So I get the k points of the n torsion, and then the k points of A. And here this is multiplication by n. And once I take k points, multiplication by n may no longer be surjective, because taking group invariance is only left exact functor. And so the cohomology measures the failure of that to be surjective. This continues like this. And of course, it goes on with H2s and H3s as well. Okay? Yeah. I mean, it has to be a sheaf for it to be representable. Yes. Well, I think the definition you gave is probably not a sheaf, but you want to sheafify it. And then I believe the statement is that in this case it's representable by the dual variety. I don't know about just in full generality. I mean, if you look in Sayre's book on class groups and what is it called? Algebraic groups and class fields. Proves this there. He discusses a few other cases there. So you'll get more there. Okay, so we had that Galois cohomology sequence. And we're just interested in actually just a piece of what I've written. So we're going to ignore this thing on the left. That's going to be irrelevant. So, so the first thing says that this map from A of k to H1 kills the image of multiplication by n. So n times ak. And that's exactly what it kills. So it gives an injection from A of k mod n A of k into that H1 of gk on the n torsion. And then this map here, the next map, it lands in the n torsion because of the exactness properties of the sequence. So this goes to, and the image is exactly the full n torsion. So this goes into H1 of gk on a k bar with an n put on the outside. So oftentimes when you're using Kummer theory, you're just using this part of the exact sequence. And in fact, we're not even going to need this piece. We're just going to need to concentrate on this piece here. So we're trying to prove that this, we're exactly trying to prove that this group on the left is finite. And here we have it injecting into another group. Right? So it suffices to prove that this group in the middle is finite. I mean, this is a long exact sequence, so the image here is the kernel here. Kernel here. But we're not going to need that anyway. Okay, so it would suffice to show that this guy in the middle is finite, but it's not finite. But fortunately, the image lands in a subgroup, which is finite. So, so in fact, there exists a finite set of places of our number field K, such that the image of this map, maybe I'll call it delta, the image of delta consists of classes which are unramified away from S. So in other words, it lands in this cohomology group H1 with coefficients in GK, I mean, H1 of GKS acting on AN of K bar, where GKS is the Galois group of the maximal extension of K unramified outside S. And so you can, I mean, it's easy to say what you can take S to be. You can take S to be the set of places where A has bad reduction, union the set of places above n. Okay, so we haven't talked about good and bad reduction of abelian varieties yet. But after we talk about group schemes in this, we'll come back and sort of see why this is true. So it suffices to show that this H1 is finite. And that is true. And here's how to prove that. So basically, it's hard to understand, it's often hard to understand H1s. There's some twisted homomorphisms from this group to that module. And so I think, whenever I want to analyze an H1, the first thing to do is to look at the field. I mean, there'll be some finite extension of K whose Galois group acts trivially on this. This is a finite module. And you want to just go to that field, because then the H1s just turn into normal homomorphisms and use the inflation restriction sequence. That's like, I guess, the dumbest thing that you can do, but often it's enough, and it's enough in this case. So let L over K be a finite Galois extension such that all the n torsion is defined over L. And so all I mean by this phrase A undefined over L is that if you look at the action of the absolute Galois group of L on this thing, this action is trivial. So there's an exact sequence that relates cohomology of GK with cohomology of GL. So you start with the cohomology of GK. Now, the absolute Galois group of L is a subgroup of GK. So you can restrict a one-code cycle to GL and get a map like this. And then the kernel of that map is exactly H1 of the finite Galois group. So in general, when you do the inflation restriction sequence, which is what this is called, you have to put the GL invariance of this thing here, but in this situation, GL is acting trivially, so there's nothing to do. And in fact, the image of this map lands in the Gal L over K invariance here, but we don't need to note that. So we want to establish finiteness in the middle. So it's enough to establish finiteness on the outside. Oh, and I wanted to put GKS here. And LS. I think it's actually finite. So this thing is obviously finite, because both the group and the module are finite. And now this thing over here, so H1 of GLS acting on this, is just isomorphic to, so this group is acting trivially on that module. It's exactly how we chose L, so that would be true. So when you're doing H1 with trivial coefficients, it's just Hom. So this is Hom from GLS into this thing. Just thought of it as an abstract group, which we know is Z mod NZ to the 2G. So that 2G you can move outside if you want. And so a map homomorphism from GLS to Z mod NZ is almost the same thing as the Z mod NZ extension though, unramified away from S. A surjective homomorphism is exactly the same thing. But then you have to worry about the ones which aren't, but whatever. And there's only finitely many such extensions. So that means that this Hom set's fine. So a fact from number theory is there's only finitely many such extensions. And that does it. Are there any questions? Okay, so I want to just kind of go over the ideas again. So the point was that we have this group that we care about, and we embed it in this H1. That's the first step. And the H1 is kind of something that you can actually analyze. The problem with doing that is that we didn't constrain the ramification. And if you don't constrain the ramification, it's going to be infinite. So you have to figure out in what way you can constrain the ramification, and then if you do that correctly, you get something finite, just appealing to facts from number theory. So the thing that we're working towards at the moment is what I called theorem B in the first lecture, which was to show that certain abelian varieties have rank 0. And we're going to use something similar to this, but we're going to have to restrict the ramification even further. We're going to have to understand exactly how far down we can go and in what way we can modify it. So that's how this idea is going to show up again. But we have to talk about a lot of things before we get there, like neural models and stuff. But I just want you to kind of keep this idea in mind. All right, so then there's one final thing that I want to talk about today, which is something I meant to do last time. So I'm flipping back. And that's the isogeny category for abelian varieties. All right, so the first thing that I want to prove is called Poincare reducibility. So this is the following. So suppose that A is an abelian variety and B is a sub-abelian variety. The statement is, then, there exists a sub-abelian variety C such that the natural map from B times C to A is an isogeny. So if you try to think of abelian varieties as kind of linear things, which they sort of are because they're abelian groups, this is like saying you have some abelian variety, think of it as like some kind of module. Here you have some sort of submodule, and this is saying that there's something like a complementary module, basically, is the intuition here. And so here's the main idea of the proof. I'll leave it to you to check the details. So we have so I guess I never said this, but you can quotient by abelian subvarieties and get an abelian variety. So you have this quotient map, A to A mod B. And there's a map on the duals in the other direction. Like this. But now since these are abelian varieties, you can choose, there's not a canonical one, but you can pick polarizations. So there's an isogeny like this. Choose an ample L. And then I'm just going to define C to be the image of this thing in A. And so it's obvious that it has the correct dimension, and then you can check that these properties actually. So that's how you find C. Definition of things. So I mean, the way that I would begin by defining C is like the sheaf quotient. And so that's obviously a sheaf in the right place. I mean, if you had it over like k bar, then since A and B are defined over k, there should obviously be some descent data down to k. So if you only knew how to construct it over the closure, I think it should be easy to descend it down. But in general, for me, the way that I mean, talking about quotients can often be confusing when you're dealing with group schemes and things like that. And it's very clarifying to kind of first consider the sheaf quotient. And that's always defined kind of in the right place. And then it's just a question of representability. All right, so a definition. Our abelian variety A is simple if the only sub-abelian varieties are 0 and A. So a corollary of the reducibility theorem is that given A, any abelian variety, there exists simple abelian varieties, say B1 to Bn, and an isogeny from the product of the B's to A. And the proof is simple. Either if A is not simple, then by definition it has some sub that's between 0 and A. We call that B. And there's a complement. Both B and C are going to have smaller dimension, and so by induction, you're done. Yeah. The degree of the polarization. What do you need? I mean, so the factor is going to be unique up to isogeny, first of all. Two factors are isogynous. And if I'm taking C to be a sub of A, I guess the minimal one is just going to be the connected one. I mean, I guess I've only considered connected ones, but I mean, perhaps, I guess. Yeah, then I don't really know actually. I mean, there is going to be a minimal degree of a polarization. There could be many polarizations of that degree. I don't know how these images are going to compare. So there's a way to sort of a formalization which makes these results a little bit pretty. And I think it's useful in terms of how you think about things. So I'm going to, I'll make this a definition. So I'm going to define a category. So I'll call it isog is the following category. So the objects are Abelian varieties over K. And the Hams in this category between two things, A and B, are the Hams just as Abelian varieties. So maps of varieties that are also homomorphisms, tensored with Q. And you can check that there's a well-defined composition, just the obvious one. So this is called the isogeny category. So you can show that if you have an isogeny from A to B, that there exists an isogeny in the opposite direction, from B to A, such that the composition, let's do GF, is just multiplication by n for some n. So on elliptic curves, you could just take G to be the dual of f, but generally you have to use a different construction. And so this implies that 1 over n times G, which is not actually a morphism of Abelian varieties, but it makes sense as a formal map in this category, is the inverse to f. So this category isog is, I guess it's the universal category in which isogenies become isomorphisms. So you can also show, this is not very hard, that this category, isog, is an abelian category. And this Poincare reducibility theorem is then just basically equivalent to the statement that this category is semi-simple. And so two consequences of this point of view, which you could probably prove directly very easily, but this makes it very clear, is that, first of all, the decomposition of A into a product of simple abelian varieties is unique up to isogeny. So what I had written here before I erased it was that you could find B's that were simple such that A was isogynous to the product of the B's. And in fact, the B's are unique up to isogeny. So if you pick B primes, then each B would be isogynous to B prime. And the reason for that is that this isogeny category is a semi-simple abelian category. And whenever you have such a category, when you decompose an object into simples, those simples are unique up to isomorphism. And so the second consequence is that if A is a simple abelian variety, then if you look at its endomorphism ring, tensored with Q, this is a division algebra over Q. And again, that's just, whenever you have a simple object in an abelian category, and you look at its endomorphism ring, at least if that ring contains a field, then that ring is automatically a division algebra over that field, just for formal reasons. Okay, any questions? Okay, well then this sort of concludes our overview of elliptic curves and abelian varieties. Next time we're going to start on group schemes. And I'm going to try to give more complete proofs in that part of the class.